So I just want to give you a quick refresher on what we talked about last class, which is Newton's method for approximating the roots of a given function. So what we're going to imagine here is that we've got just some kind of function. Doesn't really matter what it looks like. The only thing we're going to require, at first anyway, is that it does have some root that we can actually try to approximate. So let's give this function a name. Let's call it f of x. And what we're going to do here is we're going to start off with some initial guess. Right? We don't know exactly where that root is. You know, maybe we know it's somewhere in the interval from 1 to 3 or 1 to 10 or something, which we could figure out using the intermediate value theorem, which we've done a bunch of times by now. So we don't know exactly where it is, but we do know sort of roughly where it is, right? We know that it's in some sort of interval. And so what we can do is make a sort of educated guess as to where we think this thing is sort of reasonably located. That's kind of the idea. So what we're going to do here is make some sort of reasonable initial guess. That initial guess we're going to call x naught, x sub 0, and this is just going to be our initial guess. Now, what we can do here is take our initial guess and actually plug it into the function and see what we get. Right, so we trace it up to the function, that's what we get there. And by plugging this in to the function f of x, we can see that we didn't actually correctly guess the root, because in this case, f of x would actually be some positive quantity. And so we didn't actually get the root correct with our initial guess, but we didn't really expect to. So what we do is this system by which we sort of incrementally work our way closer to the root. Step by step, we want to inch closer and closer to this root. And that way we can say that we've sort of correctly approximated where it actually is. So the way we're going to do this, first we need some way of finding another x value on the x-axis. And so what we're going to do is start off by taking a tangent line. Whoops. So we're going to take a tangent line. There's our tangent line there. And we're looking, right, just from this picture, we're looking for some sort of x value which is closer to the root than what we started with. And if we look here, well, right there, right, the x-intercept of this tangent line is closer to the root than x naught was, right? It's closer than our initial guess was. And so we're going to mark that point. We're going to call that x1. Right now, we're going to check and see, okay, is x1 actually the root of the function? So we plug it into the original function. That gives us this output value down here, right? Whatever height this function, whatever height this point on the graph is, that would be our output, f of x1. And we see that we get some negative value. In particular, we don't get 0, so we're not actually sitting on the root right now. So what we do is the exact same procedure again. Let's find the tangent line without breaking our chalk this time. And so there's our tangent line to the function at x1. And now if we're looking for another x value that's even closer to the root than x1 was, well, do the exact same thing, and right there, the x-intercept of this second tangent line is indeed closer to the root than x1 was. All right, so we started off with an initial guess, sort of an educated initial guess, which was x naught. We find a tangent line and calculate its x-intercept, call that x1. That is also not equal to the root, right? We didn't sort of hit the nail on the head with that one. We get some negative value here, so we just do the procedure again, right? We find the tangent line, find its x-intercept, which is this blue point, and indeed we're even closer to the root than we were before. And so what we're going to do is just continue this process again and again, right? This is going to be what we call x2. We're going to go up to the function. We get some positive value when we plug it in, so we know we didn't get the root exactly correct. And we find the tangent line to the function at x2. We get some other value here, which, they look really darn close because chalk is an imprecise thing here. But they look really, really close. But the idea is that we are Still not exactly on the root, but we're really, really close, right? That's really the idea. And whatever this x-intercept is here, we would call it x3, and repeat the procedure for x3 and x4 and x5 and so on. Ultimately, this is going to give us a sequence of x values, which, at least in this picture, are sort of going to continually ping-pong back and forth right next to this root, getting closer and closer and closer every single time they do it. And this is the essence of how we're going to use Newton's method. I mean, this is Newton's method right here, figuring out these x values. Using this algorithm, which we're going to talk about in the next video, we can actually go ahead and pretty closely approximate roots of functions.